Now let's look at the anti-Markovnikov addition of water across a triple bond. With the internal alkyne, we're not going to see a difference in the product outcome using hydroboration-oxidation or the acid-catalyzed hydration. However, we will see a difference in the terminal alkyne. The internal alkyne will be converted from an alkyne to a ketone. You'll see that the mechanism really looks the same as when you do this process with an alkene. You get the boron on the one side and a hydrogen on the other side. And then during the second step, the oxidation step, wherever the boron is where the hydroxyl group ends up. Of course, we know that enols are not stable, particularly in the presence of acid or base, but this time we're in base, so let's look at how the tautomerization occurs. There's a deprotonation at this position, and then the electrons here are going to move down, kick these guys over, and you end up with a carb anion formed here. And that's going to get protonated by the water, which is acting as a solvent, and so this is how you end up at the ketone. Once again, this is an equilibrium process, but it does favor the keto form heavily. With the terminal alkyne, you're going from an alkyne to an aldehyde product. The steps are going to be the same with the terminal alkyne. It's just that the boron is going to have a preferred side this time. It's going to go to the less substituted side due to sterics. And so in the end, you get the hydroxyl group on the less substituted side. And after the base catalyzed tautomerization, you're going to get an aldehyde product. Once again, in the case of the symmetrically substituted alkyne, you're going to get the same product no matter which side gets the hydroxyl group. But again, in the case of the asymmetric alkyne with the ethyl and methyl group, for example, you will get a mixture of products. And once again, there's no stereochemistry to consider in this process.